Okay. Guys, welcome back. Let's continue. Can you hear me well?
Yes, sir. Yes.
Who are you? Who are you?
I'm Rick, sir.
Rick. Here we have Somoni Rick, Kim Chung, and Chan Makara, Sidaro, Sarah Ritz. Sarah Ritz is trying to join. Guys, if it is okay, I'm teaching without showing my face. If you want to see, I mean, if you want me to turn on the video, I can do that, but also I want to see your face. And since I don't see you, that's why I'm teaching like that. Is it okay, or you want to have a kind of video lesson? I mean, do you want to see our faces? React, what do you think? Are you there? It is fine like this.
Yes, sir.
Okay. Guys, if you have different suggestion, feel free, okay? Because when I actually turn the video on, always there's a picture, but anyway, I cannot see you, and it is covering some part of the screen. That's why I'm not actually turning the video on. Okay, good. Guys, let's continue. Two things left from this chapter 2.4. Now we'll talk about applications. Applications of what? Systems of linear equations. And after that, we will see another method, iterative method for solving linear systems. Okay. So actually, really, when we talk about application, okay. All right. This linear system of equations, they have a lot of applications in many different fields, like solving chemistry equations in physics, in business, a lot of applications. That's why we cannot talk about all the applications here, but just we have a few examples to give you some general idea how they are used to solve real life problems or problems that's actually we face. Okay. So first we will talk about allocation of resources. A great many applications of systems of linear equations involve allocating limited resources subject to a set of constraints. So that is one application of system of linear equations. So you have a kind of limited food source, for example. Let's say you are feeding something here in this example, you will see that we will talk about a bacteria, okay? So then we'll try to find the best solution to this problem. I mean, the best, what is it, allocation of these resources. So in this example, a biologist has placed 3 strains of bacteria, denoted 1, 2, and 3, in a test tube, where they will feed on 3 different food sources, A, B, and C. So immediately we are talking about some kind of, here we have tube, right? The first one, and this one is the second one, and this one is the third one, and each tube contains some different bacteria, right? That is bacteria type A, bacteria type 1, 2, bacteria type 3. And also we have 3 different types of food, food A, food B, and food C. So each day, 2,300 units of A, 800 units of B, and 5,500 units of C are placed in the test tube. And each bacterium consumes a certain number of units of each food per day. Okay, so actually we have 3 different types of foods. And from A, we have 2,300 units, 800 units of B, and 5,500 units of C. And we just place them in the test tube. Okay, how many bacteria of each strain can coexist in the test tube and consume all of the foods? Okay, here, if you just tabulate this, Actually, here it's a given. Here we have food A and food B and food C. Bacteria strain 1, bacteria type 2, bacteria type 3. Right? So food A, in bacteria A, we have 2 units, and bacteria B, food B, 1 unit, and here we have also food C, 1 unit. Right? What does it mean? It means that type A in 1 day it eats 2 units of food A, right? And it is 1 unit of food B, and it is 1 unit of food C. And what are A, B, C? You can just think that this A is kind of rice, let's say. B is, let's say, chicken. C is amount of water. Maybe this one is 2 grams of something, 1 milliliter of something, and 1 milliliter of something like this. Okay. And also bacteria, strain A, the second type of bacteria. It is 2 units of food A in 1 day, 2 units of food B, and 3 units of food 3. And bacteria 3, that is 4 units of food A. It doesn't consume food B, and it consumes 1 unit of C, right? What is the question? Now, how many bacteria of each strain can coexist in the test tube and consume all of the foods? Okay, guys, here, let me just draw your attention to this. Here we are talking about a test tube, so our tube is only one. These are 3 types of bacteria, right? This one is, here we have bacteria, and then what bacteria, and we are putting everything in one tube. Okay, and we are feeding them with 3 different types of food A, food B, and food C. Okay. So how many bacteria of each strain can coexist in the test tube and consume all of the food? So if you just give 2,300 units of A and 800 units of B and 1,500 units of C, if you just put this in the test tube, and we know that they are eating rates here, right? And what food and what bacteria is eating here, how many bacteria of each type we have to put in the tube so that they can consume all of this food in a day. So to do this, assume that from the first type, let's say we should put X1 bacteria. From the second type, X2 bacteria. Third type, X3 bacteria. So here, the first type, X1, X2, X3. Then from here, food 2, right? Actually, this one is 2 units of food A. The second one is 2 units of food B. Food A. This one is 4 units of food A. And how much food A we have? 2,300 units. So here we have 2 times X1 plus 2 times X2 plus 4 times X3. And they eat this much food. And how about food B? It is 1, 2, 0, right? The first type, second type, third type. And we can form this equation. So they will eat this much food. In similar way, I can form the third one. And after all here, we get what? A system of linear equations. So to answer this question, we have to solve this linear system. And we know how to solve this from the previous sessions. Immediately, we can use Gauss-Jordan methods to do this one. Let's form our augmented matrix. Okay, here I need to delete this. Okay. So just for explanation. So that is our augmented matrix representing the system. Here we have 2 to 4, 2,300. That's the first row. 1 to 0, 1 to 0, and 800, right? 1, 3, 1. So also we know how to reduce this to reduced row echelon form. If you actually using elementary row operations, we can reduce this to this reduced echelon form. So as you see here, actually from type A, we need to put 100 bacteria. From type 2, we need to put 350. From type 3, we need to put, what is this, 350 bacteria. Then if you just put this many bacteria in a tube and put all of this food, there will be no food left at the end of the day. That is one application of system of linear equations in allocation of resources. All right, let's say another similar example. It says that repeat example 1. using the data on daily consumption of food units per day. Assume this time that 1,500 units of A, 3,000 units of B, and 4,500 units of C are placed in the test tube each day. So that means that what we are changing here, we are just changing the right-hand side, right? We are just changing this part of the equation. Everything is the same. How about if we have different units of food of each type? At that time, first, we need to write our, yes, also table. Okay, repeat example 1 using the data on daily consumption of foods. Okay, and also according to this table. Now, using this table, we can form our system again at x1 plus x2 plus x3. These are 1, 1, 1, right? And 1, 2, 3, 3,000, and 1, 3, 5. Here we have 1, 3, 5. Here we have 4,500. And here we are assuming that in a tube, and we have just x1 of bacteria 1, x2 of bacteria 2, x3 of bacteria 3, right? And we are just giving them food A and food B and food C. So the question is, if our allocation is this much, right? And what must be the number of those bacteria? That's a problem. And we form the equation. And after that, we have to solve this. And again, you know how to solve this. First, we need to form our augmented matrix. That is, what is it? A, right? And here we have constant vector. That's our augmented matrix. And here we have 1, 1, 1, 1,500. That is 1, 1, 1, 1,500. 1, 2, 3, 3,000. 1, 2, 3. And similar way, it is this. And again, by using elementary row operations, we can reduce this to reduced row echelon form. Here we will have that thing, right? So now we need to solve this equation. How do you solve this? Because as you see here, we have free variable because one row is only zeros. So if you just write the system again here, that equivalent system, here we have x1 minus x2 is equal to, from here is equal to 0. From the second row, x sub 2, sorry, this one is x sub 3, this one is x sub 3 because the third one, x sub 2 plus 2x sub 3 is equal to 1,500, right? And that means that here we have one, what is this, free variable here. What is that thing? That thing is x sub 3. So now let's say x sub 3 is equal to t. So if you substitute here, then x sub 2 will be, what is it, 1,500 minus 2 times x sub 3. That is just, what is it, t, because x3 is equal to t. And from here, x1 is equal to just x sub 3, that's equal to t, right? So the solution will be here then. The solution will be x1, x2, x3. That is equal to, what is x1? It is t. x2, 1,500 minus 2t. x3, that's equal to t. Or we can just write it as 0, 1,500, 0, and plus t. This vector right here we have, it is the coefficient of t, it is 1. Here we have -2, here we have 1. So here we have 1, -2, here we have 1. Okay. Actually, we know from here that since this x1, x2, and x3, they represent the number of bacteria in this tube, right? That means that this x1, x2, x3, they must be, what is it, whole numbers, maybe 0, 1, 2, 3, 4, 5, 6, right? So the first observation is this t must be non-zero, okay? And also from here we can see that also this 1,500 minus 2t it is a number of bacteria type 2. Also, this should be non-zero. Now from here, if you solve this, what we have here, T is less than or equal to 750, right? Okay. All right. So that means that from T is greater than this, less than this, I can just write this inequality then. This T is greater than 0, less than 750, right? What does it mean? That means that starting from 0 inclusive, right? How many possible solutions we have? Here we have 751 different solutions of this system. Okay. So for in 751 different ways, I can place bacteria of these three types into this tube so that they can consume all of this, what is it? The foods. Okay. That is another application of, what is it? System of linear equations. Guys, let's have a break for 2 minutes. After that, I will continue. Let me drink something. Okay. Another application is in balancing chemical equations. So when a chemical reaction occurs, certain molecules, the reactants, combine to form new molecules. We call this the products. A balanced chemical equation is an algebraic equation that gives the relative numbers of reactants and products in the reaction and has the same number of atoms of each type on the left and right-hand sides. The equation is usually written with the reactants on the left and the products on the right, and an arrow in between to show the direction of the reaction. Anyway, this part actually is about balancing chemical equations, and I don't expect you to understand every word in this problem. And once again, here, I'm just showing this stuff so that you have some idea how the system of linear equation is used in solving, what is it, in balancing chemical equations. And these things are actually from high school. If you remember, the first thing is about, for example, let's say water, right? Water formula is H2O. A balanced chemical equation of the water is, let me just write here, for example, that is 2H2 plus O2. And here we have 2H2O. As here, how many hydrogen atoms do we have? 2 times 2, it is 4. So 2 times 2, we have 4. How about oxygen here? It is 2, and 2 times O, that is 2. That is very simple chemical, what is it? Reaction or equation. So something like this, okay? So in this example, the combustion of ammonia, that is NH3, and oxygen produces nitrogen, N2, and water. So find a balanced chemical equation for this reaction. So the combustion of ammonia, that is NH3, I don't know how many of this marker we need to put here, in oxygen, that's why oxygen is added, right? Produces nitrogen. Here we have nitrogen and water. Here we have water. Find a balanced chemical equation for this reaction. All right, here everything is given. Here what you have to do is, okay, if we have such things given, can we actually form our system of linear equations and determine the values of this W, X, Y, Z so that this chemical equation will be balanced, right? So as you see here, now from here, this W, this N, right? How many we have? W. On the right-hand side, here we have 2 times Y. So the first observation is nitrogen. On the left, we have W. On the right, 2 times Y. That's why here we have this equation. W must be equal to 2Y. And how about the hydrogen? On the right-hand side, here we have 3 times W, right? So that's 3W. On the right-hand side, here we have hydrogen, 2 and times Z, that is 2Z. And what is left here? Oxygen. Now oxygen on the left, here we have 2 times X. So here we have 2X. On the right, here we have 1Z, that's equal to Z. Now, As you see here, that thing is totally just, we get here mathematical algebraic equations, which is a linear because all variables are multiplied by constant numbers. So we have to determine their values. Now, if you just write this in the standard form, what do I get here? We will get w minus 2y, that's equal to 0, 3w minus 2z, that's equal to 0, 2x minus z, that's equal to 0. So we have to solve this system. How many variables we have here? Here we have w, x, y, z, right? So we have 4 variables. So that means that we will have this kind of system. So here 1, 2, 3, 4, and that's a homogeneous. That's why I'm not writing the last column. And here we have 1, 2, 3, 4, and here we have 1, 2, 3, 4, right? So if you just form our augmented matrix, we will get this thing. Here we have W, right? Here we have X, here we have Y, here we have Z. That is actually our 0 vector. So the coefficient of W in the first one, it is 1. X we don't have, that's why it's equal to 0. Y, negative 2. We don't have Z, that's why it's equal to 2. I mean 0. In the second equation, coefficient of W, it is 3. And we don't have X, that's why 0. We don't have Y, it is 0. Z, it is negative 2. In the third one, we don't have W, that's why here we have 0. And coefficient of X, that's 2. And we don't have Y, and Z, it is negative 1, right? So that's it. That is our augmented matrix. We just write this matrix here, the homogeneous system, right? So now if you reduce this to echelon form, what we get here, here we will get that thing. That means that if I just write here, this one is W, right? So here we have W minus 2 over 3. What is it? This thing is Z. That's equal to 0. The second one is X minus 1 over 2Z. That's equal to 0. And here we have WXY minus 1 over 3Z, that's equal to 0. Okay. Actually, we have a lot of different solutions, but it's just we need to show one of them. And here, usually, we just show actually that always these coefficients are whole numbers. So that's why if I choose here, let's say here, for example, Z is equal to 6t, for example. What we have here? From here, we get W, and here 6 over 3 is 2, so W equals 4t. And how about X? X equals 6, here we have it is 3t. And how about Y? Y equals 2t, right? And actually, you have infinite many solutions, and all solutions are, if you assume that these W, X, Y, Z are whole numbers, right? They're just multiples of these numbers. So one solution is, let's say t is equal to 1, the smallest of this one. Then here we will have W, X, Y, Z, right? The solution of this one will be, what is W? 4. What is X? 3. It is 2, 6. So that gives us one solution. And others will be just multiples of these numbers, because here we have T, right? That is another example of application of what is it? System of linear equations in balancing chemical equations. All right, another one is in network analysis. All right, let's drink some tea. All right. Okay, we have 10 minutes. Let's just do something here. Another application of this one is network analysis. So many practical situations give rise to networks, like transportation networks, communication networks, economic networks, just a few of them. As a computer science student and also in computer rights, actually, that is one branch of this computer science, that is network. So for us, a network will consist of a finite number of nodes. So in this here, actually intersection of these flows, right? This one is, we have one node, and this one is Another example for a node. So network consists of a finite number of nodes or junctions or vertices connected by a series of directed edges known as branches or arcs. Because we need to know actually if you're talking about, let's say, flow of water, it is flowing in what direction? If you're talking about the traffic of vehicles, they are moving in what direction, right? So if you're sending a signal, for example, you are sending in what direction? And that's why actually we call this branches and arcs. They have to, we say that directed edges. And each branch will be labeled with a flow that represents the amount of some commodity that can flow along or through that branch in the indicated direction. And again, when we say flow, it's not only about fluid, right? It may be a flow of people, it may be a flow of bacteria, or it may be flow of blood, or it may be a flow of, what is it, vehicles in a certain direction, or water, anything, or let's say internet signals. So the fundamental rule governing flow through a network is conservation of flow. What does it mean? It means that at each node, the flow in equals flow out, right? So that means that here, if you're talking about water, right? So the amount of water that flows through this pipe in 1 minute, it must be the equal to the amount of water that flows through this pipe and this pipe in 1 minute. Or if you're talking about, let's say this one is one-way road, right? One-way road, and here it diverges into two directions, all right? And here, let's say in a certain period of time, let's say here we have 30 cars passed. That means in a certain time, actually the number of cars that actually travels through this road and this road, their sum must be equal to 30, right? And also if you look at this example, this one is flow in, this one is flow out, this one is flow in, right? So that means that from here, that F4 should be equal to F1 plus F2 plus F3. Okay. So describe the possible flows through the network of water pipes shown in the figure below. Now from here, as you see, node A, what do we have here? Here flow in 5 plus 10, right? That's equal to F1 flow out plus F4 flow out. So that gives us the first equation, F1 plus F4 equals 5 plus 10, which is equal to 15. And how about node B? Here, this F1 is flow in, right? This one is flow out, that's flow out. That means that this F1 should be equal to 10 plus F2. That is 10 plus F2. And how about node C? This one is flow in, flow in, flow in, flow out. That is 5 plus F2 plus F3. It should be equal to 30. F2 plus F3 plus F5, that should be equal to 30. And the last node, here we have node D, flow in, and flow out. That is F4 plus 20 equals F3, right? Now, if you have to solve this equation, as see here, we form, what is it? A system of linear equations. Now we have to reorganize this and write this in a standard form, right? And after that, we need to form our augmented matrix. This one represents F1, this one is F2, this one is F3, this one is F4, right? So here we have F1, F4, that is 1, 1, others 0. Second one, F1 and F2 is 1, negative 1, others 0. Okay, so we know how to solve this. Now here we have augmented matrix. Here we have, what is it, B. It's not homogeneous because our constant term vector is not equal to 0. So if you reduce this to reduced echelon form, we get that thing. From here, we can write that F1 equals 15, F2 equals 5, and F3 is equal to 20, right? And we have F4. Okay, not like this. Sorry. We have 4 minutes left. Okay, I will finish soon. From this, here we have F1 plus F4 is equal to 15. Second one, F2 plus F4 is equal to 5. Third one, F3 plus, not plus, it is minus, So it is minus F4 is equal to 20, right? So as here, we have 1, 0 row, right? Rank of this matrix is less than 4. So we have one free variable, that is F4. So let's say F4 is equal to T. And also we know that T is non-negative. So what we have here then? Here we will have F3 will be 20 plus T, and F2 will be, this one is 5 minus F4, that is T, and F1 will be 15 minus F4, that will be T, right? So we know that actually these are just flow of water that is greater than or equal to 0, 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 right? So now if you just solve this from here, T is greater than or equal to 0, all right. Now from here, T is greater than or equal to negative 20, and we have nothing to do here. We know this already here is positive. From here, right, that means that T is less than or equal to 5, right? And from here, T is less than or equal to 20. So the common solution of this one is T is greater than or equal to 0 and less than or equal to 5, right? So we now have a complete description of the possible flow through this network. If T equals 0, actually we will get one possible answer. If T equals 1, another possible answer. If T equals 2, how many different, what is the choice that we have here? Here we have 6 different options. When T equals 0, 1, 2, 3, 4, and 5. Okay. Guys, that much is enough for today. Thank you very much. Once again, you just keep preparing for your quizzes, okay? Anytime you may have quiz from chapter 1 and chapter 2. And most probably you will have quiz from chapter 1 this Friday, okay? And from chapter 2, maybe next Wednesday or Friday. And after that, you will have midterm. Okay, if you have any question regarding this class or homework and anything, you may actually write in Telegram, all right? For today, that much is enough. Thank you very much for your attention and patience. See you tomorrow. Bye-bye.